This is Stump the Energy Nerd, part 2. The energy nerd hasn't changed. The audience is going to be different, I think. Today we had a pretty active group, and I'm sure it'll build as people finish their lunch bags and roll in. Mr. Nerd's ready. Okay, who's got a question?
Hi, Martin. I've got a question about vent stacks. Vent stacks, really don't like them. I've seen in a few houses where people are using air admittance valves, and I'm kind of wonder why that's not used more. It seems like a pretty elegant, simple solution.
The basic answer to the question of why don't we see more air admittance valves on plumbing, drain and waste systems, I think the simple answer is the building code. And why don't plumbers like them? There is a one-way valve. It is a mechanical device that could fail, whereas a plumbing stack that goes through your roof can also fail if there's a bird's nest in it, but besides the bird's nest problem, it's less likely to fail. And I think, really, I don't think it's any more complicated than that. My understanding is in the areas where building inspectors allow air admittance valves, it's usually only for an island sink. It's almost never, as far as I know, for the main plumbing stack for a toilet. But that said, if you live in rural Vermont or in rural New England beyond the areas where building inspectors roam, then you can do whatever you want.
Out here in Western Mass, your ideas on heating buildings, I'm really concerned about carbon dioxide, so I don't want to burn fossil fuels. What do you have for suggestions?
You're talking about an all-electric house in Western Massachusetts, and are you asking what about space heating, domestic hot water, or something else?
Space heating.
Space heating, I think that answer has pretty much been settled, ductless mini-split air source heat pumps. And the main disadvantages to these devices is it's a point source heat. I mean, if you have a very well-insulated envelope and can get your total heating load down to 12,000 BTUs an hour or somewhere in that range, you put one in the living room and you're done. In theory, with the following caveats. Your bedrooms will be 5 to 10 degrees colder when you close the doors. And if you have a long stretched out envelope with funny L's, you're not going to get even heat distribution, and you're going to get customer complaints if you're selling the house to a fussy customer. So then you have to think about 2, 3, or 4 ductless mini split heads, and that gets expensive. And the alternative is a ducted mini split system, which is available at an energy penalty or an efficiency penalty because the duct actually cuts into the efficiency significantly. But I think, ductless mini splits is the way to go for an all-electric house in New England for heating, right down to northern Vermont, where you occasionally hit 10 below zero if you get the Mitsubishi Hyperheat model.
A comment that I would make on that, I'll make a comment occasionally, I guess, and this time it would be that where you have point source heaters and you are trying to do this inexpensively and cost effectively, let's say, it's important to manage your client's expectations around those differences in terms of distributed temperature differences within the house, because that's the way that kind of system is supposed to work. You get benefits for it, but you manage your client's expectations around that, and then, presumably, you won't get the complaints.
Under what conditions should I install a solar hot water system?
If you live in an off-grid house, if you're talking residential, solar, thermal, I can't think of any other application. I think even electric resistance water heater plus PV beats solar thermal right now because of the lower maintenance costs, the similar capital costs for a complete system, and the simplicity, and the fact that you have 100% of your energy production being banked on with a grid-connected PV system, and you don't have that, imbalance between production and use that you have with solar thermal. The question was, what about warmer parts of the country? To some extent, if you live in a climate that has no need for freeze protection, like the southern tip of Florida or Hawaii, then the cost of solar thermal systems goes down. And it could be argued that they make more sense. The thing about sunnier parts of the country is not only do you get more solar thermal energy, you also get more PV energy for the same size system. My solar electric system in Vermont, the same system would produce twice as much energy in Arizona for exactly the same dollars invested. So if I believe that PV makes sense, it makes twice as much sense in Arizona as it does in Vermont.
I have a neighbor who uses an outdoor wood boiler. All judgments on that aside. So all winter he has free scavenged hot water, and all summer he's got a indirect system off his oil boiler. So if I can get him to switch, and he's highly mechanical, and I think he can probably do it all by himself. So if he can install it for under $3,000.
If he's highly mechanical and installs it himself and is mechanical enough that he can fix the pump when the pump goes down and check the glycol level and replace the glycol level when it has been overheated and the pH is changed, and he's willing to, do all that maintenance, why not? Of course, I put one on my roof for the same reason. But on the other hand, why put up $3,000 of solar thermal equipment when you could put up $3,000 worth of PV?
There is also the consideration of electric resistance heating for hot water is pretty tough on the utility, big peak loads. Power goes out, you still got your solar thermal cranking away, especially if you got a PV-driven pump system, which is what I like to use on them. They can be made to be very reliable, steam back design, don't have to worry about your fluids. So there's a lot of different ways to do it where you can have it. If you can do the installation yourself, you've really cut the cost dramatically, because in the solar thermal, the big cost is installation, no question.
Those are excellent points, and I certainly agree about the dependability when the grid is down. That's an important point.
Are you stumped yet? We're working on it.
I will let the audience decide whether I'm stumped.
No, I'm not trying to stump you, but just make a comment on the getting domestic hot water from either solar thermal or PV. And I agree with what you said about if the priorities are simplicity, cost, reliability, durability, it looks like the PV to make electricity and then heat the hot water makes sense. But some people might be really concerned about, the carbon footprint and think about primary energy, or source energy, in which case, and I have a PV array on the roof of my house, but we have to realize the only reason we're all doing this, and it makes sense, is we have a very artificial situation because we have free, 100% efficient daily storage and seasonal storage that's created by the financial structure that says we get the same credit for any kilowatt hour we use any time of the year for every kilowatt hour that our PV array sends in. And that solar thermal is different than that. So if you're really caring about your carbon footprint, solar thermal, you are getting that energy from the sun when it's made.
That's a good point, and I agree as far as the fact that the grid, by its very nature, currently has a carbon footprint. We're all hoping that we're on the path to making a transition where the grid will have a much lower or a zero carbon footprint. And whether or not we ever get there, I don't know. In terms of taking advantage of the net metering opportunities, you can't really fault people to take advantage of net metering opportunities, because if any of us were in charge with creating utility regulations, we would all agree that net metering is a wonderful thing that helps us all. So why shouldn't we take advantage of it? It's a great system. It's a social good. And there's no downside right now. So, of course, it behooves us to take advantage of it if it works for our particular conditions.
I've got my eyes on the prize here. This is to stump you. So my question is, where does one find a high-performance, high-quality HVAC contractor?
You stumped me. Let me think, though. Michael Chandler. He's in North Carolina.
Okay.
I just have a comment. I heard a speaker last year who's in the PV business, buying and reselling large amounts of power. And he was saying that it makes more sense to have PV in New England than it does in Arizona because the rates are so much higher here than they are in Arizona. So you said it makes more sense in Arizona. He's saying just the opposite. It actually makes more sense here.
Well, you can do these economic analyses any way you want. And as John Straub said at his session this morning, if you tell me what results you want, I can create a spreadsheet that proves exactly what we want to prove. If you're trying to lower, if you want to prove that the investment is wise, of course it's wisest in a place with very high electricity costs, like Long Island or Hawaii. But the current grid cost of electricity is kind of a political accident. So, I mean, if you want to look at the kilowatt hours per year is another way to look at it. I mean, there's a lot of ways to look at it. I'm off grid. So I made the decision to get PV. The current cost of grid power is irrelevant to my decision. So there's just a lot of ways to look at it.
Okay, a question that I'm currently stumped about has to do with the use of exterior rigid insulation on above-grade walls. We'll say climate zone 5.
Could you put the microphone closer? I can't.
Yep. Exterior rigid insulation, let's just say climate zone 5, above-grade wood walls, 2x4, 2x6. And when I started asking myself this question is when I looked at the Energy Star version 3 specs, which one way to comply with their reduced thermal bridging requirement was R5 on the exterior. The 2009 IEC calls for, it allows you to remove the above-grade, interior air barrier class 1 if you have R7.5 on a 2x6 wall, right? Where I get confused is, okay, so EPA says one thing, R5, you're good to go, but they don't address that interior above grade, in warm side of the wall air barrier, or vapor barrier, to be more correct, I guess. The question I have is if you have, let's say, a class 2 vapor retarder like craft face bats, and would you recommend that those reduced R values like an R5 on a 2x6 wall would be appropriate in our climate zones, or should you still go for that R7.5 or R11 2.5 to reduce the risk of condensation? So class 2 is where I have no idea what to do with.
Excellent question. There's two components to the question. One is the fact that the code allows exterior rigid foam in certain climate zones at a level that is not thick enough to keep your first condensing surface above the dew point and is therefore dangerous. And the code is just plain stupid in this situation because a wall assembly shouldn't be code legal if it gets you into trouble. And the second question has to do with what's the appropriate vapor retarder on the inside. So to take the first question first, there's another section of the code which you alluded to that allows you to have a reduced vapor retarder performance for certain wall assemblies if you have exterior rigid foam. That's the chart to pay attention to. And that's the chart that is reproduced in my blog online called Calculating Minimum R Values for Exterior Rigid Foam. And if you follow those charts, and I think for Climate Zone 5, 2x6 walls, did you say it's R7.5? And then if you go up to Climate Zone 6, it's 11.25, something like that. It obviously varies between 2x4 and 2x6 walls and Climate Zone and gets more stringent as you get colder and as you have a thicker wall. Follow those and ignore the R5 minimum allowable assembly in the chart that gives you the minimum R value requirements in the code. If you have exterior rigid foam, the basic rule is you should never have interior polyethylene or vinyl wallpaper. And if you avoid those two materials, almost anything else works. Craft paper works, vapor barrier paint works, and membrane, which is a smart vapor retarder, and other similar smart vapor retarders from Europe also work. So does that answer your question?
The ones that I was still questioning was those ones that were considered class 2, and you had just said that something like craft face. If I had a builder that wanted to use the R5 1-inch exterior insulation, and he was only going to put craft face bats in the interior cavity, would we create a issue there? But basically, you're saying
no. I mean, the craft face vapor retarder is flexible enough because it itself is a smart vapor retarder. If it ever is in a damp situation, it will it will change to a higher permeance, and therefore that allows interior drying, which is good.
Just wanted to ask if that also goes for what we were just talking about, flash and bat, when they flash
yeah, if you follow the same guidelines for flash and bat as I recommend for exterior rigid foam, you're safe. If anything, you've got a little more leeway because the flash layer takes up some of the compartment that would otherwise be filled with fiberglass. Therefore, your fiberglass has a little bit lower R value, thereby warming the flash layer, which is to your advantage. So yes, you can use the same rule of thumb.
What do you do with a dryer in a house, in a really tight house? How do you accommodate that?
Well, the standard passive house approach is a condensing dryer. The condensing dryer sprays a little cold water on the airstream that's circulating through the dryer, and the cold water actually condenses the moisture that's in the air of the drying clothes and sends everything down the drain. They started in Europe. They're now available in America, and some, I think at least 1 or 2 American appliance manufacturers make them as well. If you don't want a condensing dryer, you can just put up a clothesline, exactly, inside, outside, in your basement. And you're still adding moisture to your house, so that may not be something you want. With a condensing dryer, the water at least goes down the drain.
Well, two follow-ups on that, just to see. First of all, how much water are we using in those things? And secondly, how big a load can you dry at once?
They take about twice as long, so you do have to be patient. The drying time is extended. It takes a trivial amount of water. It's, you're just spraying a little bit of cold water so that the water vapor has something to get cold, to condense on. It actually condenses on the water droplets, I think. I think the aerosol spray is not on the clothes. There's some type of chamber whereby the air is circulated from the clothes drying area to a condensation area, and that spray creates more condensation, so the amount of water that goes down the drain is more than the amount that's sprayed.
So you're not substituting an excessive use for an excessive energy use.
I think that's correct.
Okay.
I was at ResNet last week, and Sam Raskin was talking about this issue, and apparently in Europe, they have heat exchanger dryers. And I asked him after the session, it was ESCO and LG both make them. And when I tried to find those online, I could only find them in Europe.
Those are heat pump dryers?
Yes.
Right. I've heard of heat pump dryers. They're very expensive.
I did have one of those dryers. It was it might have been an ASCO, actually. This is about maybe 7, 8 years ago. And it used a heat exchanger in the base. So you basically blew the exhaust through a heat exchanger that was drawing air from the house through the unit. So it's kind of nifty because all the electrical energy was being dumped back into the house as heat. So I thought it was a really nice way to do it. My wife didn't agree. The heat exchanger plugged very quickly with the lint, so you had to continually clean this thing out. It was a maintenance nightmare. So that one didn't work out.
Hi there. I'm interested in building in northern climates like Wisconsin. And I'm thinking about ventilation with a ERV. And on the Green Building Advisors website, all of the ERVs that I've been looking at seem like when the temperature starts getting really cold, you're going to have some kind of damper or electric frost protection. Are there any units, and sorry, this might be a little bit leading, but are there any units that I don't have to invest in these auxiliary frost protection systems?
As far as I know, you don't have to invest in a separate system because most ERVs and HRVs that are sold to cold climate areas already include the controls that allow the defrost cycle. And this has been routine for 20 years. And most defrost cycles, I mean, the downside is you don't get outdoor ventilation air or a very reduced amount of outdoor ventilation air during cold weather. For a certain number of minutes each hour, they actually just close a motorized damper and circulate indoor air through the coil to defrost it or to raise the temperature so frost doesn't form. You got a follow-up question?
So my answer to that is, so for example, Renew Air has their unit that operates at 4 CFM per watt, including their intake, exhaust and intake air, and seems to be able to do all of that without having to close dampers or add any electrical auxiliary heating. And their units are like $600, and I don't know why that isn't some.
So just so I understand, most units don't use electrical resistance heat to solve this problem. They recirculate indoor air, which is already warm. But some units may use electric resistance. But are you saying that the Renew Air?
Yeah.
The Renew Air unit does not require any kind of defrost cycle?
Exactly. They go down to minus 12 degrees.
Well, if so, that's great news. I didn't know it. I don't know if that counts as stumping, but that's a product that sounds very useful.
At what point in this climate do you think or you understand that it's better to buy a PV generating electricity or energy than it is to invest in an envelope strategy that reduces energy? Where's the balance point, let's say, for a wall? What size of a wall, what type of a wall, in your experience, is equivalent to the cost of a sufficient PV to offset the heat loss at that point?
Well, John Straub did some calculations at his workshop or presentation, I should say, this morning on that topic. And the basic answer is it depends. It depends on the cost per R of your wall as you add additional thickness. And as he said, the cost is all over the place depending on the cost of your labor and the cost of your materials and the construction of your wall assembly. Somewhere between R20 and R40 is what John said. And the equation can be done mathematically pretty easily. You can find out what $1,000 invested in PV will generate in kilowatt hours per year, and then you can calculate with a energy modeling program how many kilowatt hours you will save per year by adding $1,000 worth of insulation to your walls once you know how much your insulation costs. And I think it's an excellent calculation to do, even if it's on the back of the envelope. But the final question, Bruce, is whether we should call these equivalent technologies. And some people say that PV and insulation shouldn't be considered equivalent because the PV doesn't last as long as the insulation. So the Passive House crowd argues, with some justification, that we should invest in insulation even if it's more expensive than PV. But it's really important to do the math and make your own decision. I don't mind making the cutoff at the PV level because I think that's a good cutoff point.
Hi, my question is, how do you calculate heat losses through a crawl space given insulated perimeter walls, uninsulated crawl space floor, and an uninsulated barrier between the occupied space and the crawl space?
The short answer is with an energy modeling program. PHPP probably is as good as any at this point. I wrote an article on the topic.
PHPP is
a passive house planning package. And you can buy it from the Small Planet Workshop online for, I think it's $275, somewhere in that range. And it'll take you a week or two to learn how to use, maybe longer, or you could go to a workshop and they'll teach you how to use it. The trouble with energy modeling programs is it's a huge investment in time to really get up to speed with them. And the accuracy of the answer depends strongly on how careful you are with the inputs, and a lot of them have inputs that are unanswerable, especially concerning crawl spaces and basements. Soil temperatures depend on soil characteristics, and even the water table and the way the water table interacts with the soil. And everyone guesses at those characteristics because they're important variables that are simply unknown. So there's a false accuracy or false precision in your results. And you can get the German physicists to write the algorithms, and the algorithms are based on something. But if the inputs are unknown by the user, then the Michael Blasnik approach is just as good, which is you learn from experience what matters, and you go with rules of thumb, and you're just as smart as a German physicist at the end of the day.
Yeah.
Hybrid instantaneous heaters. Are they just window dressing on an old product? I'm thinking of the Eternal, which was the first one to make it, where they have a small buffer tank inside, maybe 2 gallon, and they claim that you don't get a cold sandwich with it, it's got a very high efficiency.
Well, I'll repeat the question. These are the so-called hybrid tankless heaters that try to solve the cold sandwich problem of instantaneous gas heaters by having a small tank. I think they work. I think, though, the measured performance on several of the ones I've seen shows that they're not as efficient as the instantaneous ones, because if you keep a small tank continuously warm, there's an efficiency penalty. And the payback for these instantaneous water heaters is a long payback, usually at least as long as the equipment will last. And it really depends on whether, if you have access to gas, the question is, what's the alternative? If you don't want an atmospherically vented gas water heater because you don't want backdrafting issues, you have a more limited set of options. But basically, instantaneous gas water heaters cost so much and save so little that it's hard to make the payback work. But the cold sandwich problem is helped by the small buffer tanks, and it will eliminate those irritating phone calls from clients who say, I hate this thing.
The frost-protected shallow foundation design guide says that you need to have at least a foot of well-draining material right underneath the insulation under the slab. But if you have additional well-draining material that you have under there, you can reduce the size of the wings that spread from the edges of the foundation. My question is, what happens when you have a lot of, say, crushed stone below? We have a situation with a high water table and a lot of organic fill. We're going to have to go down pretty deep. Are there new problems that are created by having so much crushed stone with its voids beneath the slab that would bring in cold air or otherwise create problems for how much insulation you need to have beneath the slab?
Short answer, I don't think so. I've never heard of a downside to too much crushed stone. I mean, crushed stone cannot really be compacted with a compactor. If you run a plate compactor on top of the crushed stone, nothing really happens. It just kind of moves around. But if you have a raft-style foundation or a frost-protected slab foundation where you have a layer of rigid foam and a reinforced slab, you're distributing the load over a very large area. And even minor shifting of a little bit of stone should not undermine your house. Assuming that other common sense needs of a foundation have been attended to, and you're not like at the edge of a river where you'll get erosion or trying to build it up in a cliff-like manner?
Well, my question more had to do with the amount of insulation that you use in the raft beneath the slab. The wings that extend beyond the slab can be reduced the more well-draining material you have beneath the slab. If I have 4 feet of crushed stone beneath, in addition to the foot that they say you have to have, it says you could theoretically remove all 48 inches of the wings, and so you really don't need the wings anymore because you're not going to freeze beneath the slab. We have a higher water table. We also feel that removing those wings would increase the infiltration of cold air beneath the slab. That's my concern. So
right.
You see
Well,
that tension,
I guess it depends on whether the crushed stone is exposed to the atmosphere. In cold weather, first of all, you should have a cap of soil to grow grass. Second of all, in most climates, you have snow in really cold weather. All of those help. But the bottom line is the performance of your slab will always be better with thicker insulation. And, if you're worried about heat loss through your slab, R16 foam performs a lot better than R2 or R4 foam. And you can make your foam as thick as you want. And so I don't think that it will perform worse than soil, but it might. And if you think it might, you can add another 2 inches of foam.
At what point does the embodied energy in foam start to outweigh increasing its thickness?
Well, there's several people have done calculations. I don't have the embodied energy or the global warming potential numbers at the tip of my tongue. So on that level, I'm stumped. But they're easy to look up. And like a lot of people, I don't memorize everything. When I need to look something up, I look it up, and that's what Google's for. But the embodied energy in rigid foam can be calculated. Obviously, every time you add 2 inches, you get less thermal benefit, less savings of energy, and therefore it's more and more suspect. So you do reach that point pretty quickly with rigid foam, quicker in terms of R value than with cellulose. And Alex Wilson has also done some reporting on the global warming potential, and those charts are available too, published on Green Building Advisor. And if you're worried about global warming potential from the foam, then you need to pay attention to that because you can very quickly do more damage to the atmosphere by having thicker foam than if you just didn't buy it in the first place.
Martin, explain that global warming. What is it about foams of one sort or another that contribute to accelerating the problem of global warming?
The concern is with the blowing agents, and the open cell spray foams use water as a blowing agent. That's benign, and the blowing agents used for polyisocyanurate are benign. And right now in Europe, you can buy XPS, which is extruded polystyrene, which has benign blowing agents, and I think it's CO2, which is ironic because CO2 is the problem, but you get what I mean. It's not a significant amount of CO2. However, the blowing agents currently used with and EPS has benign blowing agents, currently used with XPS in this country when released to the atmosphere, have a global warming potential many times more than CO2. So a small volume of these chemicals helps heat the planet, or heats the planet in a very damaging way. The controversy is we don't know for sure exactly which blowing agents are used because the XPS manufacturers won't tell us, and they're in the process of changing them all the time. We don't know the release rate of these chemicals because we know that over 50 years, the gases near the surface of the XPS probably reach the atmosphere, but how about the blowing agents in the middle of the XPS? Do they ever get out there, and if so, at what rate? We're making guesses, we're making assumptions. So Alex Wilson's calculations have definitely been challenged. Some people say it's more guesswork than science, but somebody's at least thinking about these issues. So I've always said if you're worried about these issues, and you probably should be, just use polyiso, and if it's concrete slab, you could experiment with Roxol mineral wool. If you're feeling adventurous, you could buy foam glass if you have a lot of money like Alex Wilson or contacts in the foam glass industry, or just buy the XPS and say it's still better than the alternative.
Okay, I've got Bob. The issue here too is that these things are changing, but they're changing because the market says that it matters that we should limit the extent to which our construction materials are injurious to our health and environmental health with carcinogens and endocrine disruptors and things like that. That's becoming more of a conscious position in the industry in this country, far less so though than it is in Europe. But the more we advocate with sales reps, people out there on the floor, that we care about this, the more likely it is that we'll get the kind of foams with lower global warming potential that they currently have in Europe.
Quick question is, where does the global warming potential number come from? What makes that up?
Well, I think that we know exactly what the global warming potential is of a variety of chemicals. I don't know who did that research. I think it's done in a lab. And what Alex Wilson was reporting was the known global warming potential of a presumed blowing agent. So the uncertainty was, is DuPont really still using that blowing agent? And they won't really reveal the exact, but if they're not telling us with great fanfare that it has no global warming potential because they're proud of it, we can assume that they're hiding it because it has a huge global warming potential. So I'm guessing Alex Wilson is close to right.
This is another foam question. It relates to raft slabs and exterior foundation insulation. I know that there are there are things you can add to EPS, for instance, like borates that protect against animals chewing on it, insects, whatever. But I haven't heard how long that lasts, and I've seen a lot of insect infestation and rodent infestation on exterior foundation insulation, and it makes me nervous when I see all of the details that I've seen here and I've seen for many years of people putting foam around houses, because I've done that myself, and I've seen this happen. So what's your take on all that?
I think it's an excellent point, and I think the risk is real because most builders who've been out there for a while have pulled apart houses and found insects in foam. Like any building decision, it's always a risk-benefit decision, and there's no perfect exterior insulation yet. I think I'm at the point now where I think you can minimize worries about insects in foam by keeping everything dry, keeping foam, that is on an above-grade wall, separated from grade, reducing the danger as much as possible. But, people who say I'm really worried about foam and I want to design a foam-free house, I respect them a lot. There's a lot of unknowns about how long all of these building materials will last. So I think all of the experience you've shared is worth considering when we make those decisions.
Thank you all for coming, by the way. And thanks to the Energy Nerd. Thanks to Bruce for helping out. Enjoy the show.